Hey guys, so there's an easier way now. Alright, so there's now an easier way to find our Stat 200 page because people can't find it unless it's bookmarked. So if you go to the Department of Statistics and you click on the faculty and then you click on me, here's our website. So if you happen to lose the URL, you can always do that. Now I just want to show you one thing that we added to our calendar, and that's that at the start of every week, I show you what you need to review in Stat 100, from Stat 100 material. So you can just click on these, and for example, here for this week, there's these two chapters that you can review, and if you click here, you can see some Stat 100 video lectures as well. So this is what we're starting today in our notes. So if we go to the document camera, actually, why don't we watch this short video in preparation for our lecture. So let me just find it here. It's kind of a fun video, just a few minutes. We'll watch this before our lecture. Okay, here we go.
Hey, my name is Tyler Vegan, and I'm here to talk about spurious correlations. You might have seen some of my charts based on a program I wrote to find correlations between completely unrelated sets of data. For example, there's a correlation between the divorce rate in Maine and the per capita consumption of margarine in the United States. And there's a correlation between the number of worldwide non-commercial space launches and the number of sociology doctorates awarded in the United States. But what does all this mean? Anyone can plainly tell that there's not actually a connection between margin and merit. But everyone considered the hypothesis for a split second and said to themselves, are we launching sociologists in space? And that's the part that's so cool. We were scientists, if only for a moment. We saw data, we formed a hypothesis about that data in the form of a causal mechanism, and then we rejected that hypothesis based on our personal experience with the world. That's a big deal, and that's the part that computers can't do. Research is about discovery. But only humans can actually make discoveries, so computers are a great tool. The purpose of the spurious correlations I show is not to say that data is ambiguous, and you can interpret it however you want. No. Statistical data can show correlations, and then it's up to us as rational thinkers to establish whether there's actually a connection between the variables, or if it's merely a coincidence. We do this in two ways. First, we need to mathematically prove that correlations really exist. Scientists have much more sophisticated methods of determining whether two variables really correlate by using p-values and significance. But I am not an expert on statistics and number theory, so I'm not going to talk about that part here. Instead, I'm going to leave that to another YouTuber, like Singing Banana, or Numberphile, or Byheart, to make a video about it. And when they do, I'll link it here. Second, to establish a connection between two variables, we need to establish the why. The why is usually called the causal mechanism. The causal mechanism is like the verb in a sentence connecting two things together. For example, there's a correlation between how many videos I've watched by Science Show Space and how much I know about space. The causal mechanism is that Hank and Caitlin are teaching me more about space. The teaching is the verb, and it's causing me to know more about space. Finding causal mechanisms is the key goal of a lot of scientific research, because when we find causal mechanisms, we learn that much more about the world around us. Sometimes we see a correlation that we can't explain, and it might inspire us to search for a potential cause. A good example of correlations leading to conclusions is the connection between smoking and lung cancer. In the early 1900s, the incidence of lung cancer was on the rise, and no one really knew why. Then, in 1929, German physician Fritz Licken published a paper in which he showed that lung cancer patients were particularly likely to have been smokers. That is, there's a correlation between smoking cigarettes and the incidence of lung cancer. That paper led to a lot of research in which we learned about the dangers of smoking, but it never would have happened if someone hadn't seen the correlation and then researched. To sum up, correlations are a great starting place, but it's up to us to be critical of the correlations that we see. Correlations between two variables could be merely coincidence, or they could be the result of an underlying causal link. And every time we see a correlation, we have a marvelous opportunity to try to figure out which one it is. I'm Tyler Vegan. Have a great day.
Okay, so, that was a fun video to watch. And if you look at our notes on page 31, where we're starting looking at scatter plots and regression, simple linear regression where we just have two variables, you'll see right here that this scatter plot is one of those crazy coincidental correlations that I actually took from Tyler Vegan's website. And what we have here is this basically an accidental association. It's a pure coincidence found by searching databases, mostly on a time, what he's looking for is two trends, two time trends that are pretty much identical. And he does this, these are just completely accidental correlations and they seem so crazy. Like this is one between the number of people who died by becoming tangled in their bed sheets and the total revenue generated by skiing facilities. And you can see even the little, look how beautifully they match up. So this is, he said, okay, so these are complete coincidences. They actually, he has a whole lot of them on his website because he searches many databases to find exactly this. So this is one extreme he talked about, and the other extreme he talked about was there's smoking and lung cancer, which is a clear causal connection. So he talked about basically these two extremes. And I like that he said that we really need to think about, we really need to use our minds, our brains to, we can't just rely on computers or these significance tests to figure out causal connections. And so, but most of the action in this course, most of the real problems fall in between these two. For one thing, these things are just, we don't care about these are, we would never see this connection if we weren't searching databases. And this one, we already know is clear causation, okay? So basically, we're in this middle ground here where we have to look for it. There's a reason for, it's not pure coincidence. There's a reason for the connection between two variables, and that reason is confounding, that maybe there's a third variable driving those two. So there is a reason for it. It's not just a coincidence. So let's look at those two. That's what we talked about last time. And that, for example, here's a clear case of confounding, where both variables are caused by a third variable. We talked about in our notes last time, we talked about lighters being a confounder for the smoking being a confounder for this association we see between people who carry lighters and people who get lung cancer. We said there's this association, people who carry lighters get a higher incidence of lung cancer, but it's not the lighters that are causing them, it's smoking, that's the lurking variable. Here's a very classic example that you see a connection between ice cream sales and drownings. The more ice cream that's sold, the more drowning there is. But is ice cream causing people to drown? No. What is? High temperatures, right? I mean, the picture would be like this. You'd have a picture where you could get a scatter plot where you see this correlation like this between the ice cream sales and drownings, the number of drownings. Okay, ice cream sales and drownings. And you can see this positive correlation. But obviously, do you think that ice cream causes people to drown? No, what's happening is, but it's not just pure coincidence. There is a reason why you're seeing these two connected, right? And that's really where we use our brains.
And that video sort of missed that middle ground. This is where we have to, and this one's pretty obvious. Both, you know, when it's hot outside, high temperatures, cause people to jump in swimming pools, maybe even when they don't know how to swim. So it's gonna cause drownings. We're gonna have more accidents, boats, etc. And also it's gonna cause people to drink, to eat more ice cream. All right? So that's an obvious one that we can keep in mind as an example of confounding. Now, the ones that we're really concerned about are much more complicated than that. For example, health and wealth. Does being, you know, we talked about this last time a lot. Does wealth cause health? You know, or does health cause wealth? You know, there's probably, you know, it's probably, you know, both of those things are probably going on. Or is there some factor, third factor like education in particular, learning statistics, that drives both of them, right? Drives both health and wealth. Or a mixture of all three, which is most likely, and it's very difficult to tease out what's going on because there's so many causal loops going on there. All right, and then we have the case of clear causation. So I just wanted us to, a lot of what we're going to be doing this course is trying to figure out causation and regression models where there's a lot of factors and a lot of possible causal connections, and trying to tease out what could be the confounders here. So, any comments about that, about the video, or about what we're doing here? Okay, so let's just move on. And so today we're just going to be talking about simple regression, right? And this is a review of what you've had in step 100. So when you have a scatter plot, you have just two variables, an x and a y, and you have a scatter plot. There's all these little points here, and I'm just, you know, idealizing it with this sort of elliptical shape here. That follows a roughly linear trend. And we can fit a straight line through the data. And this is called the regression line right here. This is the regression line. It's also called what's called the least squares line because it's a line that minimizes the sum of the squared distances, these vertical distances, the actual y's, the distance between these actual little points, this distance would be the actual y's, and the regression line is our predicted y's. And it minimizes the sum of the squared distances. Another way to think about it is, another way to think about the regression line is a line that estimates the mean of each vertical, within each vertical strip. So for example, we'll have a lot of x values here, and of course they don't all have exactly the same y value. If they did, by the way, they'd be on this line, which is called the SD line. This is the SD line, so maybe we should think about that first. This SD line, if there was a perfect correlation, so if r was equal to 1, or negative 1, it would just be a line sloping downward. This, if r was equal to 1, then all points would lie on the SD line. So what is this SD line? It's the line that goes through equal numbers of standard deviations in x and y. So for example, this is the point of averages where these two lines cross. This is our best predictions for y given x. And this is the line that is basic. This is the line of equal standard deviations. If we were in z-scores, this is the zx equals zy line. Zx equals zy line. What do I mean by that? Like, if there was a perfect correlation, say, between height and weight. Now, height's measured, let's say we have a height measured in inches and weight's measured in pounds. So what does it even mean to say there's a perfect correlation? Those numbers aren't going to be the same. What do we mean by that? They're in different units. So you can think of this standard deviation line as measuring how close these points hug a line in standard units. So we have a standard measuring stick, which would just be how many standard deviations you are above or below average in both height and weight. And if there was a perfect correlation, then people who are the same number of standard deviations above average in both height and weight would fall on this line. There'd be a perfect correlation. So for example, if you're exactly one standard deviation above average in height, I would predict that you'd be exactly one standard deviation above average in weight. So your rankings, is if we ranked you all, it's not only the order, like rank you from smallest to tallest, from lightest to heaviest. It wouldn't only be that your rankings would match up, but it would be the spacings between them would also match up. How many standard deviations you are above or below average. And that's what it means when we say that there's a perfect correlation. That's what we mean. Now, there usually isn't a perfect correlation, right? So you'd think, this is not our best prediction. You can even see from the shape of this cloud that way up, Okay, so you can see that there's usually not a perfect correlation, there isn't here, and you can see that this line right here would not be the line that would best predict our y value from our x. Here, you can see, if I made let's look at this. Okay, so if you have, let's say these were heights, and I'm trying to predict weight, then all these people in this vertical strip are the same height. Now, what weight should I predict them? The line that has the perfect correlation way up here would way overestimate. You know, we'd want to predict somewhere in the middle. In fact, the regression line is the best fitting line through the average of each vertical strip. I'll show you this in a minute on the computer, in the data program. You'll see this nicely illustrated, but for now, just think about it. Basically, what this regression line is the line that, sure, minimizes the least squares line. It minimizes the squared distances here from the actual y's, all these little points, distances to the actual versus minus the predicted, these distances. But it's also, you can think of it as basically the average within each vertical strip. All right, that's what I say up here. The mean value of y at each value of x is another way to think about it. And you can see here, it's going to be below a perfect correlation, and here it will be above. And this is always going to be true, because think about it. If there was a perfect correlation, every single person would fall on this line, correct? What if there was no correlation at all? It was just random scatter, just totally random scatter. Well then, what would be your best prediction? For example, let's say, do you think your height has anything to do with how well you do your GPA? Do you think I can predict your GPA from your height? What do you think the correlation coefficient is there? Do you think there's any correlation between people's height and their GPA? No, so it's just 0. So then, if this was height and this was GPA, then our scatter plot would just look like a random, like we just threw the points there, right? And then, if you had to guess, what would be your best prediction? If I know your height, since it doesn't tell you tell me anything about the GPA, my best prediction would be the average height, no matter where you were. You could be tiny, the average GPA. You could be really short, you could be really tall, but my best guess would be just the average for everyone. So it'd be a completely straight line through the average. And what this, usually we're in between. We're in between a total zero correlation and perfect. And so this slope of the regression line right here, this slope basically indicates how close we are. It's always going to be somewhere between 0 and here, 0 and 1, or 0 and -1. And how close it is to the standard deviation line, well, that's R. Let's look it up. That's our R value right here. So if we go over 1 standard deviation in the x direction, we only go up R, a factor of R, which is less than between -1 and 1, right? That fraction of the standard deviation line. So let's write that down. So the regression line, I just said, is always less steep than the SD line, correct? Less steep, because it's a mixture of no correlation and perfect correlation. So it's less steep than the SD line, and less steep by what factor? It's less steep by a factor of the correlation coefficient of R. Right? And R is always between -1 and 1. So when R is exactly 1, the two lines are the same, or -1, it would be just a slope down the same. And when R is 0, it's just a line through the average. All right, so let's just look at, so this brings us to, that's exactly what I'm saying here. The slope of the regression line is R over the standard deviation, R times the standard deviation of Y over the standard deviation of X. Slope, you've learned this back in 8th grade, is rise over run. So if you go 1 standard deviation in the X direction, you're not going a full standard deviation in the Y direction unless R was 1. But usually, if R was 0, this would be your best guess. But here I'd say R looks to be about 0.5, so you're about half the way up. So if you go 1 standard deviation in the X direction, right, however many, you do not go 1 standard deviation, but R times. You wouldn't go 1. So there's your slope. Okay. Now let's see what else. Let me show you, any questions about this? Does this make sense to people? Not if it does. Okay. So, let me give you some visual. Why don't we take, let me just make sure, let's see. Okay, let's see. Why don't we, I want to illustrate these vertical strips here. So why don't I go to the computer here, and let's go to our data program. And why don't we look at this data set that we're going to be looking at on the next page, or one very similar. It's going to look at predicting final exam scores. It's called the grades if you want to find it, right here. And we're going to look at a scatter plot. It's the same one that's on the next page in your notes. And we're going to, on the x-axis, we're going to look at, we'll have our the exam averages for the former Stat 100 class. And on the y-axis, we have their final exam scores. And you can see, doesn't that look like a positive correlation to you? Now let me show you. So here's the regression line, and here's what's known as the standard deviation line. And the correlation coefficient here, R, is 0.5953, about 0.6. So can you see that this regression line, this blue line, is about 60%, 0.6, 60% as steep as a perfect correlation? because the correlation is 0.6. Like a lower correlation, like homework, would have a less steep line compared to the standard deviation line. Here our correlation is only 0.4, right? Let's see what labs would be. Let's go back to exams. All right, so let's get rid of this. I want to show you what I mean by this being the best fitting line through the means of all the vertical strips. So let's get rid of this. And now what I'm going to do is create some vertical strips here. So, okay, so let's make it so you can see what's going on. All right, so in this vertical strip, we only have one person who scored like, what, 55 on the exam, that sucks, and about, what, 70 on the final. So this, and there's a little horizontal, well, the mean of just the average of just 1 point is right there. Now we have two people. These people here scored about a 58 on the, all right, that was their exam average. But look at the disparity. One really did terrible, 55 or something on the final, and the other one did quite a bit better, 72 or something like that. So this, we have 2 points, and you see this little horizontal blue line is the average between those 2 points, etc. Now we have a lot more points in the middle. Now, obviously, you can't fit one line all the way through there. If you could, if they were lined up so you could, well then that would be our regression line. But here's, it's the best fit through those. So it fits pretty well in the middle, but sometimes at the ends it's not fitting as well. That's one way to, a nice intuitive way to visualize what the regression line is doing. Any questions on that? Okay. So now we're going to take a look at these numbers here. You see that I have a very similar data set in the notebook. I just pretty much rounded the statistics here. These are the actual statistics, and n is 107. So I sort of, basically I did approximated them on our example. And so we're going to get something very similar to this. We're going to see how we can use these 5 summary statistics, the average, the standard deviation, and the correlation coefficient, how we can use those to get this regression equation, and how we can use it to get something called the standard deviation of the errors, which is basically the spread around this regression line. You know, if you go 1 standard deviation of the errors, you get about 2/3 of the points, and if you go 2, you get about 95% of the points. Very similar to our normal curve. All right, so let's go back to the overhead, to the document camera. But let's just finish up here, because I didn't talk about what did we do. So now you know how to compute the slope. It's right here. And you won't get this formula in the exam, so you better know it. Right. Okay, so now I want to talk about that spread around the regression line called the standard, the typical error around the regression line. It's the standard deviation of those errors around the regression line, the vertical distances between the actual y's and the predicted y's. And it's this handy formula, the square root of 1 minus r squared times the standard deviation of the y's. Another way, it's also known as the root mean square error, because that's the same thing. Here's the errors, you square them, then you take their average, and then you take their square root, which is exactly how you take a standard deviation. All right? So these concepts, summing these mean square errors in r squared, are key statistics that you're going to see over and over again when we do analysis of variance. That stands for analysis of variance, and we're going to begin that in chapter 11. All right, so what you might have learned in previous statistics classes is that you can think of r squared as the proportion of the variation in the y's that's explained by the regression line, and you can think of 1 minus r squared as the proportion of the variation of the y's that's left in the scatter around the line, the errors. We'll talk about that in just a second, but first I want you to just look at this formula and at least give you an intuition in the extremes of why it works. So, let's just check this out. This is what I want to explain. And of course, when you solve for 1 minus r squared, that's what I did here, that's where you get the proportion of the variation of the y's, or the variance, that this left, that is the proportion of the errors over the total variation of the y's. That's what 1 minus r squared is. Okay, but first let's just look at this and get a good visual. All right, so what are we going to look at here? So when r is equal to positive or negative 1, then when it's equal to 1, let's just plug a 1 in there, then what's the standard deviation of the errors? You can do that. The standard deviation, put a 1 or a negative 1 in for r, and what do you get? You know what you get, right? What do you get? 1 minus 1, right? 0. Okay? And the picture would look like what? When r, let's just look in the first quadrant here, let's just do this positive 1. It just means if you have a perfect correlation, there is no error. Every single point is on the line. So there is 0 error, so the standard deviation of the errors, all the errors are 0, so their standard deviation has to be 0. And that checks out. Fine. Let's look at the other extreme. When r is equal to 0. Okay? When r is equal to 0, then what happens? When r is equal to 0, you get what? That the standard deviation of the errors is exactly equal to the standard deviation of y, right? You have just 1 times the standard deviation of y, and let's see if that makes sense. That's the situation we just talked about before. We said when the correlation is 0, it's just like, imagine throwing the points down in a random pattern, just like raindrops falling, just like no pattern at all, okay? And now, what does this mean? Now, our best prediction, no matter what x is, since x tells us nothing, we might as well just guess the average of y. So we'll do that, put it right there, and that's the average of y. That line would be your best predictor. And then, do you see how those two things are exactly the same, right? What does stand for? Okay, so do you see how now this is our prediction line, and the spread around this, the standard deviation of the errors, the spread around the prediction line is exactly the same thing as the standard deviation of y, because the standard deviation of y is spread around the average of y. Right? It's the deviations, the standard deviation around the average of y, and the deviation of the errors around the prediction line are exactly the same thing. So just from an intuitive point of view, at least at the extremes, it makes sense, okay? Questions? Right. So, now, how does this r squared and 1 minus r squared, let's go back to this. We'll go back to this in a minute. When we summarize, when we sum things up. Right now, I want to do this example. Whoa. Yes. All right, so now
this is very similar to what you saw. It's basically, I used rounded numbers here, but this is a very similar plot to what I just showed you in the data program. And I really, really encourage you to explore that data program because it makes things, really come alive. So this is our standard deviation line, and this is our regression line, right? And now, and we've got these 5 summary statistics. So the average of our exams was 83. The final average is always somewhat lower, and here it's 73.6. Don't get scared. This is how it used to be. Now, this was when we first started teaching Stat 100 and didn't know how to teach it very well. So we didn't have as high scores. All right, and now what we want to do is find this regression line, the equation for this line right here. Okay, so how are we going to do this? We want to find the slope and y-intercept of this regression equation for predicting finals. Whatever you're predicting is always your y value. And what you're predicting it from is your x. This is your independent, this is your dependent. Okay? So now we just want to find the slope. So this is just beginning algebra. So remember what the slope is. And just write it down right now in terms of r. And how are you going to remember this, right? The slope is r. If we were in z-scores, it would be r. It would be r if we were in z-scores. Exactly r. But we're not. So we have to adjust it by the standard deviations. So it's the ratio of 2 standard deviations. Now, you tell me, do you think it's going to be y over x or x over y? What is with slope? Do you think it's going to be y over x or x over y? Y over x, right? Does that make sense to everybody? Okay, so I don't want you, this should just be, if you forget it, just reason it through. Put the r down, if we were in z-scores, and then you have to adjust it because we're not in z-scores here. Okay? SDY over SDX. So that is your slope. So, now that's given to you here. Right here. You can't, that's your equation here. And so you need, in order to figure out the slope, you'll need these 3 things. So you look up here, and clearly, there's R. Now, SDY over SDX, which is y and which is x? They're labeled exams and final. Remember, what you're trying to predict, is the y, right? So you look here at the standard deviations, and what you're trying, so it's 10.3 over 9.2. Does that make sense to everybody? Not 9.2, that's the most common mistake people make, they just switch those. But think about what you're doing here. Okay, often the units will help you, but in this case, since they're in the same units, you just really have to think about what you're trying to predict. So you have 10.3 over 9.2. That is it. And then you just do that, and I got 0.67. All right, so now you know the slope right here. And since this equation is true of every single point on this line, we just need 1 point to plug in for final and exams, just one point, and then we can solve for our intercept. Okay? So what point do we know? If we're given these 5 statistics, we'll always know this point right here, the point of averages. You'll be given, from these 5 statistics, this is how you'll get your intercept. All right, so all you really need to do is plug in the averages in this equation. So plug in for the final, what's the average for the final? 73.6 equals 0.67. And what's the average for the exams? 83. And then that's plus your y-intercept. Okay? And I can just write y-intercept here. That goes right there. So what is our y-intercept? Our y, to solve for this, and I got 18. Okay? So that, 17.99, but I'm rounding to 18. Almost 18. So there's our equation. Any questions on that? All right, it's pretty close to what you saw in the data program, but of course, we had different, I rounded all these. Okay, so now, all you want to do, now you can use this regression equation to predict somebody's final score from their exam score, right? Of course, it's not going to be perfect, but that's our best prediction. So let's use it for somebody who has an exam average. Remember, these are their 3 midterms averaged together. That's what I'm saying, who has an exam average of 90. They didn't just have one exam, they had 3 exams, and this is the average of their average exam. All right, so let's do that, and so what would we get? We want to just say the final, we want to predict somebody's final for somebody who has a 90. And we're just using our equation, and I did that, and I got 78.3. So before, just to make sure I didn't make a careless mistake, let's just make sure it looks correct. So what we're doing is we're taking somebody who has, this must be 90, does it look like? Pretty much, like, pretty close. So this is the point right here, 90, 78.3. Okay, any questions on that? All right, so now our next question says, do you think this prediction will be exactly correct? Well, maybe for one person, probably not for anyone, because I didn't even give 3/10 of a point, so it's not exactly correct. But no, so of course not, but there's a range here. Now you can visualize the range by looking at within this vertical strip of 90, I'm creating a little 89.5 to 90.5, a little 1 unit strip here. You're going to have a number of different points here, and that is our best prediction. But we want to describe 78.3, give or take what? Imagine you're in this situation. Imagine let's say we had this regression equation from past data, and you said, hey, I got a 90 on my final. Ellen, could you predict, just from past data, how I'm going to do on the final, because I want to know how much I have to study. And so I said to you 78.3 is my best prediction. Well, it would make a lot of difference to you. You'd want to know, give or take what? Give me some wiggle room around that. If I was pretty sure it was 78.3, give or take 0.5, you'd have that would be a super accurate prediction versus 78.3, give or take 20. You could go all the way up to 98.3 or down to 58.3. So you want to know the range. That's super important. So we have to get some basic, that's the standard deviation of the errors. So do you think the prediction will be exactly correct? No. Let's add some wiggle room to that prediction, a range. We always want to do that in statistics to give you some, a range, not just a point estimate. So we'll use the spread around the regression line to do that. You saw that. That's what I did on the data program when I showed those bars. About 68% of the points were within 1 standard deviation of the errors from the regression line. About 95% of them were 2. Okay, so remember, how are we going to remember what the standard, and this is another formula that you're going to have to remember. So let's look at this. How are we going to remember this? The standard deviation of the errors. Well, it's like the standard deviation of y. If the standard deviation of y is 0, that would mean everybody had the same final score. There'd be nothing to predict. I could just tell you right off the bat what it is. So the bigger the spread in the y's, the bigger the spread in your errors is going to be. And then you have to factor in the square root of 1 minus r squared. And you should just check in your head, if you write this down, that, okay, when you have 0 correlation, they're the same. And when you have a perfect correlation,
you have no error. Now it should turn to 0 on, just to make sure, right? So let's do this, and we get the square root of 1 minus, the correlation is 0.6, so it's 0.6 squared. Notice that's always going to be between 0 and 1, right? That's what we just said. It has to be between 0 and 1, and this is, it's about 0.8. It is 0.8 times the standard deviation of the what you're trying to predict. You're saying my final score is going to be 7. My best prediction is that, give or take, some spread around the final, so you better be using the same standard deviation there. You're predicting final, so that's the standard deviation, of course, that you want. And it's going to reduce that. If there's any correlation at all, your error is going to be smaller here. And so make sure that you get a number smaller than your standard deviation here. Okay? Does that make sense to everybody? Just, maybe I should say, this must be between 0 and 1, which of course means that this answer has to be less than or equal to that. Okay, so now I'm saying, now let's attach some wiggle room. Okay, so now let's just, what I mean by this is just attach or give a range plus or minus 1 standard deviation of the errors. Just simply just do that for, okay? That's all I'm asking. Attach that wiggle room, this amount right here, to our estimate in B. Excuse me, B is right here, to this estimate. Right? There. All right, so let's do that. So all I'm doing is 78.3 plus or minus 8.24. And the way you want to write that is as a range, you know, some value to some value, and put the lower one first. So 78.3 minus 8.24, that's 70.06, that's 78.3, did I do that right? Minus 8.24, yes. And then the upper, 78.3 plus 8.24. Okay, and so what's that? That is 86.54. All right, so any questions? This is really basic. I just want to give you a good foundation before we go on and do, we're just doing descriptive statistics. We're not making any inferences here. We're just saying, okay, this is the data we have, and we're just describing what we see. We're still in descriptive statistics. All right, so let's read the summary here. And these summaries are really useful for you to read. They're very helpful in studying for the exam. So let's just make sure. All right, so let's look at this r squared and this 1 minus r squared that we have here. And because it's going to feature in quite a bit. It's always, this r squared's always included in every regression analysis. In all the printouts, everywhere, you're going to see this r squared. And when we're in simple, okay, so let's write this down. So r squared is always included in all regression analysis. And why do I have a capital here? Because in multiple regression, it's going to be the correlation between your predicted and your actual values. Here, it's the same thing as our little correlation coefficient squared. It's just the correlation coefficient, little r squared. the way that I so if you look at this, r squared and 1 minus r squared, you can think of it this way. I mean, this makes sense. This is your, basically your multiple correlation coefficient, or in simple regression, just your correlation coefficient squared. So you can think of this as sort of the strength of the association, the strength of the signal, the pattern. And then 1 minus r squared is everything else. That's the strength of the errors. So you can think of this part as the strength of just the random scatter, or the strength of the noise. And obviously, together, they're equal to 1 or 100%. So the ratio between the two of them is going to be the factor that we're going to be, that's going to be the heart of our statistical significance test, the chi-square test, the F test, etc. And we're going to be using to see if there's any signal at all, if there's any correlation at all in our multiple regression equation. Multiple in our data. All right. Now, any questions on that? So this is to come. And now on this page, why don't we just do a little intro to statistical inference, so you can just picture it. And I'm going to let you out in about 5 to 10 minutes so you get out early. But before we start this, you see smile is the first time ever this semester. I know, I've been bad to you. I've been just keeping you all, okay. Let's leave early, so let's get to it. So, we're going to be talking about inferences here. So far, we've only used regression descriptively to analyze the relationship between two sets of numbers by drawing a scatter plot and calculating the correlation coefficient and the slope of the regression equation. All right, now we're going to use, we did this in Stat 100. I suppose I should put that up for everybody to see, just to refresh. We haven't done that. We didn't do that today. We did this part. Now we're going to use regression to make inferences about a wider population from what's known about our sample. Back in Stat 100, we used sample averages and percents to estimate population and averages and percents by computing standard errors and building confidence intervals. Just like, polling, political polls right now. Yeah, that's what they do. From a sample, from a random sample, they estimate how the whole population is going to vote. And we looked at how to do that in Stat 100. We never did that with bivariate data, with two variables, relating two variables. We just took the average and of our sample of one variable, like how many people are for Trump, let's say, in our sample, to predict how many people will in the whole population would be for. So, but now we're looking at two variables and the relationship between them, and we want to see if that, from our sample, how we can use our sample correlation in our sample regression equation to estimate the correlation in the regression equation in the whole population. All right, so now let's use our same exact example, but let's suppose that these 100 Stat 100 students, the same exact, was not the entire class, but a random sample from a much bigger class. Let's say a class that had 2,000, and we wanted to use the sample, this randomly selected sample, to estimate the correlation of the entire population. How would we do this? How can we use the sample correlation and slope to estimate the correlation and slope of all the 2,000 scores? All right, so let's deal with the correlation. I said, how can we use the sample correlation and its slope? Okay, so let's deal with the correlation coefficient. First, we're going to have to always, now we're doing inference, we always have to have a probability model. So this translates pretty nicely into a probability model, and we're going to set up a box model. All right, what do I mean by that? The box always represents the entire population that you're drawing your sample from. represents the whole population. So here we have this box, and on each, remember, it's filled with tickets, and on each ticket is written a number. So it represents the whole population of, what is the whole population? 2,000 students. So that means we are going to have one ticket for each student. So there'll be 2,000 tickets. And on each is going to be written some number. Now we have to think about it. Wait a minute. In the past it was always one number, but now we have two numbers. We're talking about the correlation between exams and finals. So each student, every 2,000, each one of the 2,000 students has, like you guys, you would have an exam average and a final. You'd have, so each ticket now has to have two numbers on it. One for each student's exam average, and one for their final. So there's two numbers here, their final score and their exam average score. On each is written an exam score and final score. Does that make sense to everybody? Okay, and so now what do we do here? So now what are we going to do? We have that, and we are going to randomly, from here, how many tickets are we going to draw out? We have 2,000. How many are we, what's our sample size? So we'll randomly draw, and that's our little n, that's what figures into our calculations. We're randomly going to draw, well, do you remember? Let's see, where does it say? Right here. That's our n. We're going to randomly draw 100 tickets without replacement. Why are we doing it without replacement? Because if we put it back, then we could get the same student twice, and these are really, we're going to get 100 separate students, right? You all follow? Okay, so that's our situation. Now we want to know, that's our box model so far. That's what we should be thinking, our probability model. And then we say, what's the best estimate of the correlation coefficient R of the whole population, the whole class? Well, what do you think it would be? We got this in our sample, so what do you think? Do you think we should, don't you think that's the most logical one to choose? Wouldn't you think that would be the best thing to choose? We take out 100 tickets and we get all these statistics. After we take out the 100 students, we calculate all this. And the reason we're doing it maybe is because it's much easier to calculate on 100 than it is on the whole population. Imagine this population was 2 million. It would be very hard. We didn't have the resources, so we randomly sample. We don't have the data on what this is. And so we take this and we do these, and this is what we get in our sample. So don't you think this would be our best estimate of what the whole population correlation coefficient would be? Would you want to go higher or lower? I mean, wouldn't that be the most common sense thing to do? Not if you think it is. Okay, so our best estimate, we'll say that. So our best estimate of, that would be the most common sense thing to do, of R in the population would be equal to R in our sample, which is equal to 0.6. Okay? And now we're going to try to put some wiggle room around that. And we're going to see, of course, that's going to depend on the size of our sample. The bigger our sample, the closer we'll get to that. And that's what we're going to do, put a standard error around that, and that's what we're going to do next time. All right. You did get out early. Smile. Okay, your homework is posted for this. It's really, really fast. It's just one problem, really easy. So see you next time.